Hello everyone, this is Rubina Akhtar Rabia, a PhD researcher in artificial intelligence from India University, South Korea. In this presentation, I will discuss our research on diffusion-based cardiac ischemic fibrosis progression synthesis and severity estimation using histopathology images. This study also introduced a FinFET-compatible AI accelerator framework, which aim to bridge the advanced generative AI with future low power and edge-based clinical deployment. So this work lies at the intersection of medical image analysis, generative AI, and nanoelectronics. So here is our motivation and problem statement. The cardiac ischemic fibrosis is a major pathological outcome of aging and myocardial infarction, we can say. So here, histopathology remains the gold standard for fibrosis assessment, where as a result, understanding fibrosis progression dynamics is extremely challenging. So this was the reason we motivated for this research, and this motivates the use of generative AI models to simulate disease progression from static histological data in this research. You can see the research pipeline and goal. The overall goal of this research is to develop a unified framework which can be model the fibrosis progression, which can accurately segment the ischemic region, and which can estimate the disease severity. Also, which can evaluate the feasibility for low power deployments in clinical deployments. So as shown in this pipeline, you can see the figure. We introduced the diffusion-based synthesis, the segmentation-based analysis, and a hardware-aware design into a single end-to-end system. Here is our dataset description. You can see the slides present in this study or in this research. These are the ischemic fibrosis patches extracted from cardiac histopathology whole slide images, where we used 5,000 Masson's trichrome-stained patches, which is 512 by 512 pixels and manually annotated by the expert pathologist from the hospital. And this dataset focuses specifically on ischemic fibrosis region, which can ensure the clinical relevance and annotation reliability. Here you can see the pre-processing workflow. As histopathology images often suffer from staining variability and unwanted noises and unwanted objects, so to address this issue, we applied a standardized pre-processing pipeline. This includes noise reduction, contrast enhancement, and Reinhardt stain normalization, which can align the color distribution of all images to reference template. These steps improve the visual consistency and enhance model generalization. Okay, so here you can see the overall diffusion pipeline. This figure represents the overall diffusion-based synthesis workflow. You can see input images are first encoded into a latent representation, where Gaussian noise is then iteratively added and removed through a controlled diffusion process. And then finally, the denoised latent representation is decoded to generate the realistic fibrosis image conditioned on different disease severity stages to compact the mild, moderate, and severe ischemic fibrosis stages. You can see the latent diffusion model architecture in this figure. So we present the architecture of the latent diffusion model where a convolutional autoencoder compresses images into low dimensional latent space. And then UNet-based denoising network operates in the latent space, which progressively removing the unwanted noises. And then finally, the severity stage embeddings are injected into the network, which enabling controlled synthesis of mild, moderate, and severe fibrosis patterns. In this slide, you can see the segmentation and severity pipeline. So after completed the synthesis progress, both real and generated images are passed through a segmentation pipeline. A UNet-based model identifies fibrosis region at the pixel level. So the resulting segmentation masks are then used to compute the fibrosis area percentage, which form the basis for severity estimation and provide us the numerical value as a fibrosis area percentage. Here you can see the segmentation module and severity estimation. So this slide actually focuses on segmentation and severity estimation. So the segmentation model accurately localizes the ischemic fibrosis region, and then the severity is estimated using clinically inspired area-based thresholds, which categorizes fibrosis into mild, moderate, and severe ischemic stages. So this approach provides an interpretable and clinically meaningful severity assessment for pathologists, researcher, and others also to detect early diagnosis for cardiac patients. This slide presents the FinFET logic architecture overview. So to enable the future edge deployment, we propose a conceptual FinFET-compatible architecture where the artificial intelligence based, the latent diffusion based AI pipeline is mapped into three main logic modules you can see in the figure. The first one is denoising, second one is segmentation, and the third one is quantification. So this design emphasizes low power consumption and hardware efficiency, which is actually suitable for medical edge devices, and it can be deployed in clinical application. Okay, this slide presents the FinFET compatible logic design. This slide details the internal logic design of the FinFET based modules. Now, we show in the previous file there are three modules. We have denoising, segmentation, and quantification. So, denoising is approximated using multiplexers, resistors, and bias control logic, where segmentation relies on the spatial filtering and comparator circuits, while quantification uses adders and counters to compute fibrosis areas percentage. Here we show the synthetic ischemic fibrosis progression from mild to severe stages. All images are generated using the same latent code with different stage embeddings to keep the research experiment fair. And then the visual results demonstrate biologically plausible expansion of fibrotic region, highlighting the model's ability to capture the disease progression patterns in this research. Okay, here you can see the synthesis and segmentation performance. So the synthesis quality was evaluated using the Frechet Inception Distance, achieving a score of 13.2, which indicates the strong similarity between real and the generated images. And also segmentation performance was evaluated using the dice and intersection over union matrix, which achieving a dice score of 91%, which demonstrated the accurate fibrosis localization. This slide have the confidence visualization and severity results to prove our research more strongly. So you can see this slide presents the confidence visualization maps, which highlighting the region strongly associated with fibrosis severity. And severity estimation achieved approximately 89% accuracy when compared with expert annotation, which actually confirms strong alignment with clinical grading from the pathologist. Here is the quantitative result tables. You can see this slide summarizes the quantitative performance metrics, including segmentation accuracy, severity estimation result, and hardware-related metrics such as gate counts and latency. This result actually demonstrates consistency between our latent diffusion model, AI-based performance, and the hardware feasibility. Here you can see the FinFET logic feasibility. Logic level simulations were conducted assuming 100 megahertz equivalent clock. The result shows compact gate complexibility and sub-millisecond latency across modules, which actually supporting the feasibility for future low-power ASIC-based deployment in cardiac digital pathology. And also you can see the outcomes. Overall, this research demonstrated a unified framework that can successfully integrate the diffusion-based fibrosis synthesis, accurate segmentation, clinically interpretable severity estimation, and hardware-aware feasibility analysis. Here I'm going to present some keynotes, limitation, and the future work of this research. So the key contribution include the realistic disease progression modeling and hardware-aware design perspective. And the limitation is this research is reliance on synthetic progression. So in future work, as a future work, we can consider that we will focus on multi-center validation and hardware level prototyping for this work. And in conclusion, this work highlights the potential of diffusion-based generative AI, which actually combined FinFET compatible design, which can enable the future edge-based low-power cardiac diagnostic systems, which can prevent or which can detect the early diagnosis, early fibrotic stages for cardiac patients, and particularly for age-related cardiovascular diseases. So here was all. Thank you for your attention and thank you for your time. So if you have any question, you can ask me.